So I see two people, two lovely young ladies in one screen. Who do we have?
I'm Jennifer and
I'm Claudia.
Oh, Jennifer and Claudia, pleased to meet you.
Yeah, nice to meet you too.
Very nice to meet you both. Would you mind giving us just maybe a quick overview of what it is you're working on?
Okay, can you read? So I'm working on GravMag inversion. So I also talked to Dom.
Excellent.
So yes, that's it. This is my master thesis.
Very cool.
and I'm working with electromagnetic data. I'm doing some survey for geotechnical characterization in my PhD thesis.
Okay.
Excellent.
And I'm focused more in time domain.
Okay. Cool. And which universities or institutions are you at?
Well, I'm at the Faculty of Science at the University of Lisbon.
I'm in a co-tutela project between two universities, Universidade di Cagliari in Italy and University of Lisbon, Instituto Superior Técnico.
Thank you. Perfect. So to get started, the first question I have is, were you able to access the notebooks that I sent around?
Yes.
Yes.
Okay. And any problems installing them or anything like that? Is that something we
No.
Okay, perfect. So then we can sort of launch right into that. And what I'm hoping, like, as we go through this today, feel free to just jump in and interrupt if you have questions, or so what I'm going to do is I'm going to share my screen, which means I won't see you. So just start talking if you have a question or anything like that. And anybody else here, like, feel free to jump in with questions or comments, and hopefully we can make this productive.
Okay.
So, just for everyone, the URL is here for where the notebooks are. So if you want to follow along, you can. So what I'm going to do, somebody's got, maybe I'm getting a lot of feedback here. Is there somebody that switched their mic off?
What?
I think, Claudia, it might be you both. Would you mind if you're just, when you're not speaking, to mute your mic?
Okay.
Okay.
Thanks. All right. So I'm just going to share my screen. Can everyone see that? Okay. So what we have here is we've got, I guess the first notebook you would land on here is this one. So this is an overview notebook. These are a whole collection of notebooks, mostly around electromagnetics, that we've put together that are sort of tutorials on how to use SimPEG. So we've got a few examples that look at forward modeling. So that's in the EM fundamentals. We've got two, and these are ones we put together last week on inverting field data. So we've got time domain and frequency domain. We'll go over the time domain one. There's also a tutorial that we published in the Leading Edge. And this is a good one for just getting a handle on some of the fundamentals of inversion. We also walk through in a lot of detail about some of the parameters and things like that, like what beta is, what that trade-off parameter in the inversion is. And so that might be one, like, these might be a series of notebooks that are worth checking out afterwards. So if we go here, the time domain EM inversion notebook, Buchmann, that's the one we want to start with. I'm also just going to open up the files here so that we have, oops. Sorry. All right, so just so that we can look at the data files and things like that. So all the data files are in data, and then here we're going to be looking at the Buchmann. There's the header file, and then we will also be looking at the SkyTem data. let's start here. I guess one other question I wanted to ask is, how familiar are people with Python? Have you used Python before?
I learned Python because my PhD. I didn't know before.
Okay.
So.
Fair enough. So like the imports and things like that, is that something you want to quickly go over?
No, the Python part I understand.
Okay, perfect. So here, these are all sort of, for people who aren't familiar, these are all sort of core packages in Python. So like NumPy does all numerical arrays, Pandas does data frames. So it's really nice for reading in like tabular data. So the data file that we have for SkyTem, this is what we'll use to read it in. Matplotlib does plotting. IPyWidgets does interactive widgets. And then SciPy has a bunch of stuff for working with sparse matrices as well as like fundamental constants. So I'm running these. So each cell that I run, I'm using Shift-Enter to run that. You can also hit the run button. So the first two, we're just importing packages. So from SimPEG, we're importing a whole bunch of things. We'll go over what each of these are. And then for the time domain EM problem, we import the time domain EM package, and that has all of the physics for simulating electromagnetic problems.
Hi, Lindsay, before you move on, what is that package, the Pi matrix solver? I never saw that before.
Okay, so this is a package that we've written. It's part of the SimPEG ecosystem, and this actually wraps solvers so that you can interact with them. Like what we can do, I'm just writing, this is pseudocode, this isn't gonna run, but if we have a_inv equals solver of A, what that lets you do is then I can do a_inv times b equals x. And so this actually just factors the matrix. It doesn't compute the inverse, it's smarter than that. But then the PyMat solver lets us do this step where we actually are treating it like a matrix multiplication. Does that make sense, Jaja?
Yes, thank you.
Okay, yeah, no problem. So that.
So Lindsay, now you chose the Paradiso.
Yep.
As your solver. So you are also able to choose something like mumps, something like that.
Yes, you can also choose things like mumps, and there's iterative solvers in there as well. Paradiso for us is the easiest install for a direct solver. So that's the one we tend to prefer for electromagnetic problems. Because like
so if you import Paradiso, you don't have to specify the name of solver in the actual calling script, right?
No, you do, and I'll show you where that comes up. So we'll keep an eye out for the term solver, right? Because we've imported Paradiso as solver. So when this comes up, that's when we're actually using Paradiso.
All right.
Okay. Cool. Any other questions there? All right. Okay, so the next cell, all I'm doing here is increasing the font size on the plots so that they look nicer. Okay, so then what we're going to do is actually look at the contents of the data directory. So here, this os.path.sep, sorry for that, but that is just, it makes this both Windows friendly and Mac friendly. So all this does, like on my Mac, is computes, actually I can show you. So it just assembles the path with the correct path separator in there. So it's nothing fancy, but that is where our data are. That's where the data file is stored. And so I'm just going to list what we have in there. So there's a few things that I've stored in there. We've got a path file that defines the river path. We have a couple header files. We've got a README. We've got some data files. And so what I'm going to do here is we're just going to look at the README just to get a sense of what's in there and what are the main files to look at. So here, we've got some information on where the data came from, when they were collected, and then importantly, the contents. So here we've got the header file for the resolve data. Those are frequency domain data. And that's what the other notebook looks like, or looks at. And then we've got SkyTem data. So we have both the header file and then the data file, the high moment data file. So what I'm going to do is we're going to use pandas to read in the data for SkyTem. So I just load that up. We're going to do pandas read table, and then we just give it the file path to our table. So we can actually look at what's in there. So if I run this list SkyTem, it's going to list all of the elements in the data header. So there's lots of stuff in there. And so what's nice about pandas is now when I've created this SkyTem object, what we can do is you can then, each of the fields that we have in the data file, so see we've got line as one column header, we can access all of the values just by doing skytem.line. So here what I'm going to do is pull out all the unique line numbers so that we can just look at what were our flight paths for the airborne EM data. And then we're also going to load the river path just so we've got something to orient ourselves. And then I've defined some plotting code just so that we can actually look at then where our flight lines are. So you can see we mostly are flying straight lines along here, but then we've got a couple tie lines. This one I think was potentially overlapping with where Resolve flew or something like that. And then we've got a few lines along the river path. So one of the things that we want to do, like if we were looking at inverting this entire data set, we probably only want to invert the straight lines and not include these different paths. And so what I wanted to do is actually find which indices those were, and we can just extract them from the data set so that we're not using them. And so you might want to do this if we're inverting in 1D or 3D. So all I did is write a little wrapper widget that let me go like line by line and see, you know, which file paths, or sorry, which lines are straight and which ones are not. And so that led me to find out that it's actually the last handful of lines that are the ones that we don't want in our data set. And so in this case, I indicated those by the tie line indices, and then we just plot everything that's not those. And so that gives us the data set that we're going to start to work with for the inversion. So at this point, we haven't actually done anything with SimPEG. This is just reading in files. But does anybody have questions about that?
Hi, Lindsay. So what was the reason again for not including the this non-straight line data into inversion again?
So what sometimes happen is if you end up with two data points that are in very similar locations, and if there's errors between them, then the inversion has to like fight between which of those two data points it trusts more. And so in this case, when they fly the straight lines, it's usually all in sequence, so the data are more consistent with each other. Ideally, you know, all of the data should agree, but they should be redundant data points, so they shouldn't be adding any new information.
Oh, so you're saying that if a straight line crosses this non-straight line, you have two measurements at same location, and you don't want that to happen.
Right.
Okay. Thank you. Yeah.
Okay. Any other questions? All right. So the next thing that I'm going to do is to just pull out some useful pieces of information for this now pared down data set. So here we're just going to look at, so with SkyTem, there's both Z-oriented, so vertical coils, and horizontal coils. We're just going to look at the vertical data. So here, the way I knew to look for Z is I looked at the header titles, and so X channel 7 is the X component, whereas Z channel 27 is a Z component at time channel 27. So all we want is the Z to compose our data set. And then we want, of course, the easting, northing, and elevation. And the way I knew to look at the laser altimeter was by going back and actually reading the header file that was included with the original data. So now we've got those, we've got our data set assembled. Okay, so now we're starting to get closer to the physics. So we know that we've got, you know, the headers were listed as channel 7 to channel 30, but those actually map to specific times. And so I just copy and pasted these values from the header file. So I can show you that. I'm just going to pull it up. So here, if we look at the SkyTem, the SkyTem Buchplanung header file, you can see there's a system description, all of that sort of stuff. We're going to end up using these values later. But then we also have where each of the channels are. So here we're using the high moment data. So we've got all the channel numbers, and then the window center, the window start, and the window width. So I've just used the center values here. So that's all this is. And then now that we've got our time channels and our data set pared down, we can actually then go ahead and plot the data at each time channel. So we can scroll through time and just see what our data set is looking like. And so now what we're going to do, we could invert, and eventually you would want to invert potentially the whole data set. But right now we're just going to look at inverting a single sounding. So we're going to pick one spot and invert it in 1D. So picked a location and then found the closest receiver to that. And so if we look at where that is, it's just this red dot here. So we're going to invert this location. And so then what I do is we're going to pull out the time channels and plot the data at that location so that we can see what data it is we're going to try and fit. Okay, so that basically up till now has sort of been all of the data wrangling, getting the data set that we want to actually invert. And now we're going to start getting into SimPEG. So the first thing that we need in order to think about inverting the data is we need to be able to forward model those data. And so what we're going to do here is we're going to use a cylindrically symmetric mesh because we have a vertical coil and we're using a 1D earth. So that's a cylindrically symmetric setup, and it's a faster forward simulation than if we were to run on a full 3D mesh. And so in order to set that up, we want to make sure, and this is important for 1D or 3D, is that we want to make sure that our mesh extends well beyond the diffusion distance, so that we satisfy our boundary conditions, because we've assumed that the fields have decayed by the time they hit the boundaries. So here, if we look at, I estimated a conductivity of 0.1 Siemens per meter. And just looking at our latest time channel, we want to be well beyond 400 meters for this mesh. So you probably want to double that, and that gives you a good idea of where you want to pad out to. So now we're going to assemble the mesh. Just please do stop me if I'm going too fast. So here what we're going to do is we define our core cell size. So that's going to be 1 meter. We have
we have a question here.
Yeah, for sure.
So we have doubts about the mesh you use. Why do you use a cylindrical mesh to perform a 1D inversion? Why don't you use like a 1D mesh?
So this case, what we could do is we could use a 1D mesh and use an analytical forward simulation. So Soggy's done a lot of work in SimPEG EM 1D, and that would work. So that's one approach that you could do there. So let me pull up. Is it all caps?
Yeah.
Oh, where's the P? There we go. So here, if you want to do a 1D inversion, this is actually where you should be looking.
Okay.
I'm just going to post that here. Sorry for the infinite loop. So that's where you should be looking if you want to do larger scale 1D inversions. Why we're using the cylindrical mesh in this case is because this is very close to what you would do in a 3D inversion. So in a 3D inversion, we're going to solve it on a finite volume style mesh. And so in this case, we define discrete differential operators that operate on this mesh. So the MT tutorial walks through that in a fair amount of detail. And so somebody's flipping notes. Command thing. Soggy, I think that might be you.
Pardon me?
Are you flipping notes or pages or something like that? Sorry, I was just getting a lot of noise on the Hangout, and I don't know who is not muted.
Oh, maybe not. That's me, I guess.
Okay. So why we're using the cylindrical mesh here is because like everything that you learn in this tutorial directly translates to doing a 3D inversion.
Okay.
Yeah. So does that make sense?
Yes.
Okay. Yeah. So here, each of these parameters, this is just sort of common shorthand that we use, but it's nothing specific to SimPEG. So CS is cell size. NCX is the number of core cells in the X direction. So we have 10 of those. And then NCZ is the number of core cells in the Z direction. So we also have 10 of those. And then we've got 20 padding cells. So then one thing that we've done, oops, sorry, this should be. So one thing that we've done in SimPEG is try to make it easy for you to define these tensor products. So this is a tensor product mesh because we can define each dimension as a vector of cell widths, and that's enough to define the entire mesh. So we have utilities under the hood that will convert this list. So this is a list of tuples in Python speak. So this is a tuple. And so here we've got our cell size and our number of cells in the X direction, cell size, number of padding cells, and then the expansion factors. So they're going to expand by a factor of 1.3. And then what SimPEG does is it's actually going to translate this list into then a vector of cell widths. So this is just a convenience. We could alternatively actually go and define number of cells in the X direction for the core region, and then define a padding vector for that and assemble the whole thing. So then here we have we're going to assemble the Z direction. So in this case, we used a logarithmically varying mesh. So the cells are logarithmically expanding in the vertical direction. And this is sort of consistent with how fields decay. And so if you look at like the magnetotelluric tutorial, we do the same thing there. But you could also just define them uniformly. And that's something you can play around with and see how that impacts both the forward simulation and the inversion afterwards. So then to set up the mesh, what we do is we're calling the mesh class, and we set up a cylindrical mesh. And then we give a list of the cell widths in each direction. So we've got HX, which we assembled here, HZ, which we assembled here. And then the one in the cylindrically symmetric mesh just indicates that, hey, we want a cylindrically symmetric mesh. You could also do 2 pi, because that is the azimuthal discretization. So, you know, discretizing a circle by 2 pi, you get back the whole circle. But here we've used 1 as shorthand just to say I want a cylindrically symmetric mesh. And then the 00C, what this is the origin of the mesh. So all that we've said is we want X to start from 0. Same thing with Y, which doesn't matter in the case of a cylindrically symmetric mesh. And then we want our Z to be centered. So here you can see the mesh is centered about 0 in the vertical direction. Oops. I should define it. And then the last thing that we do is we know that we want our active cells to be the cells below the Earth's surface. So when we're inverting, we don't want to invert for air cells. So this is just keeping track of our active indices there. No, I guess we define that twice. I define it again here, and this makes more sense here. So now that we've got a mesh, we're going to define a model, and we'll use this as our starting model, and also just a forward model to sort of sanity check that we've set up the forward simulation correctly with respect to our data. So here we're going to set the conductivity of the air cells to be 10 to the negative 8. And we're going to do just a half space Earth where we've got 10 to the negative 1 Siemens per meter. Our active cells are all below the Earth. And then we're going to also define, we want to invert in log conductivity. There's a couple reasons for this. First of all, it lets us have the conductivity vary by orders of magnitude fairly easily. It also makes sure that the conductivity always stays positive, because if you take the exponential of any positive or negative number, you get a positive number back. So the way that we keep track of all of this in SimPEG is through mappings. So here what we do is we assemble, there's going to be 3 maps. So the first thing that we do, this active map, here we've actually got just a 1D layered Earth. We have our active cells are below the subsurface. And so all that the active map does is includes the air cells. So it adds the air cells back. But that's all defined in 1D. We also need to then map our 1D model to the full mesh. And so in that case, we use a surject vertical 1D map. So it's going to take the 1D vector that we have defined vertically, and it's going to put it horizontally throughout the whole mesh. And then finally, we take the exponential so that we're now in true conductivity space. So the point of the mapping is to take whatever set of parameters you have that you want to invert for and convert them to electrical conductivity at all of the cell centers on the mesh.
Hey, Lindsay, I have a quick question.
Yeah, for sure.
So the cell mesh and the 1D mesh, do they have to have the same vertical like cell size, or like do they have to be nested or in some way?
So right now they are. If you wanted, you could define another mapping in between that performs an interpolation if you wanted to have different meshes.
Okay.
But just to use this as stated, it always has to be that the number of parameters, like this is basically a multiplication. So let me run this and I'm going to show you some things. So if we look at the active map, NP is shorthand for number of parameters. So we've got 39 parameters that we're going to actually invert for. So that's the number of cells that we have below the subsurface. But if we look at the total mapping, or actually let's look at this one. Now there's 78, right? So this outputs 78 parameters. Oh, sorry, it intakes 78 parameters. So if we look at map.shape, so basically the active map looks like a matrix that is 39 rows and 78 columns. Sorry, other way around. So it takes a vector of length 39 and it's going to output a vector of length 78.
Okay, yeah, I see.
And then here, this one will take something that is length 78, and it's now going to output something that is 2,340 long. And that is now the same as our number of cells on the mesh. And then this one is basically a, it doesn't actually change the shape, right? Because all we're doing is taking the exponential of every single parameter at the cell centers. Does anybody else have questions on this? I know that this can be like a challenging conceptual.
Yes, this part for me, it's a little bit complicated to understand. The map subject vertical 1D. I don't understand very well.
So actually, let me pull up, I think, Sagi, this is in our paper, right? I think we had a picture of it.
Yes, so there's a proceeding.
I think
no, I think we have a paper, I guess.
Yeah.
Oh, yeah,
There it was. Okay. I want that picture. Okay. Can everyone see that?
Mm-hmm.
So this is basically exactly what we're doing in this case. So we start with a model that's defined as log conductivity just below the subsurface. So this is the surface right here. Then the inject active cells adds the air cells, but that is now only defined in one dimension. Because we're forward modeling on the cylindrically symmetric mesh, we also then need it out in the x direction. We need that discretization in the horizontal direction as well. And so the surject vertical 1D basically takes this single vector and copies it
Okay.
along each cell. And then the X map just operates basically on a cell by cell basis and says, give me the exponential of each value.
Okay, now I understand. Thank you.
Yes, no problem. Are there any other questions on that?
So Lindsay, now the mapping matrix will be just one. Just like the non-zero element entry will be just one, because it's just is that right?
No.
No. Okay.
Sorry, I don't understand what you mean by just one.
Because it doesn't do any averaging, so it's just kind of spreading out.
Yes,
so it's
correct.
an identity. It's an identity. Like it's a diagonal matrix, right?
Yeah, Dequan, you're right. So, but it's not like necessarily because the 1D mapping, you need to sum that up if you think about that. Like you know what I mean?
I think, okay, so we need to break it down step by step. So in this case, when you look at like the exponential map, it effectively operates like a identity style matrix, right? It's a diagonal matrix because there's no talking between cells in order to compute, in order to take the exponential. Does that answer your question?
Yeah, so the exponential mapping is okay. I was just saying like going from like a 1D mesh to like effectively 2D mesh.
Oh,
So
yeah.
you have to populate all the cells in x direction with the same number.
Yes. Yeah, exactly. That's exactly how it's operating.
Okay, all right.
And why do we need to have the air? We are just invert for the
surface.
yes, the subsurface. Why do we need?
Yeah, good question. So we're just inverting for the subsurface, but in this case, we have to be able to forward simulate the data. So the purpose of the mapping is to go from the set of parameters that we want to invert for to what we need in the forward simulation. And so if we're simulating in 3D, so we've discretized the world, then we have to include the air cells when we model electromagnetics, because you still have EM responses in the air. In fact, all of our data in this case are being collected in the air.
Okay.
Okay. And so there's a couple other things that, like, I realize this is an abstract concept, but once you sort of get your head around it a little bit more, it's actually pretty powerful. And so if you wanted to do a parametric model or anything like that, this whole mapping framework lets you do those kinds of things. And so, yeah, you can basically take any sort of set of numbers, and as long as you can translate that to forward simulation mesh, then we can invert for those parameters. The other thing that the mappings do is now keep track of the derivatives. And so this is important when we actually are performing the inversion and want to try and make model updates, because we use a gradient-based inversion. So we need derivatives at each of these steps. And so this just keeps track of all of those. Okay, so now we're going to build a starting model. And so in this case, what I've done is we're going to just start with a half space. And it's only going to be the length of the active indices, right? Because the set of parameters that we're inverting for is just below the subsurface. And then we'll take the log of the half space. So if we look at the length of m naught, it's 39, right? And that was the same as our number of active cells. And then in order to plot it, what I do is actually, we're going to plot it in log space just because that's convenient. But to translate our model to electrical conductivity, all you have to do is multiply by the mapping. So we think of it like a matrix operator. And so in that case, this is what our starting model looks like. We have air cells that are 10 to the negative 8 and subsurface cells that are 10 to the negative 1. Does this step make sense to people? Okay, I will take silence as yes. So the next thing that we're going to start looking at is how to then set up our forward simulation. So for the time domain, we actually have a source waveform. And then this is again defined in that header file. So if I pull up our header file, we have the transmitter waveform. And so we're looking at the high moment data. And so we've used the 25 hertz high moment current waveform. So we've got our time channels. So they've started at minus 10 milliseconds. So they're basically treating like off time, or like their peak time, is at 0 milliseconds, and then they shut it off. So you can sort of see that, right? So we start at 0 and then we're building current. And so this is just in percentage. That's confusing. And then once we get to 0, we're at a maximum, and then it drops off pretty quickly. So all I've done is just copy pasted those values into this notebook. Here, we always want to work in SI units. So I've taken milliseconds and I've translated it to seconds. And then we're going to use a normalized current. So we want to normalize the current value to 1. So instead of working in percentage, we just divide by 100, and that gives us our waveform. Here, we're going to shift everything so that our simulation starts at 0. So that means we need to keep track of these 10 milliseconds. And so here, I'm just using that T0 to basically say, okay, this is how much we're going to shift relative to what they've given us. So here, then what we need to do is we need to have a finer discretization of the source waveform than what they gave us, because we actually need to be able to very accurately simulate basically as it's building up, and then as it's shut off, what's happening in those very early times. And so when things are changing quite quickly. And so in this case, we could, in order to be able to evaluate the waveform at more places, we could do a linear approximation of it, or in this case, the VTEM waveform shape is very, very similar, and we have an analytic solution for that. And then so we've just gone in and basically fit, just by hand, these values to the waveform. And so we can look at, we're going to plot that. I'll show you what each is. Let me just give you labels. So here, this is then the crew. And this is the fit. Oops. What did I do? Oh, it's because I gave these without keywords. There we go. So here we have the points where they gave us the waveform are blue, and then we have fit the VTEM waveform here in orange. Does this make sense? Do people anybody want to jump in here with a question?
I have a question.
Mm-hmm.
I have a question.
Yes, go ahead.
Can I share my screen?
For sure.
You can see here.
Oh, wait, we can't see your screen quite yet. So on the Hangout, if you go over to the left, there's a green button. There we go. Now we can see your screen.
You can see here is my program. Here is not have the source waveform. Can I add the code to here?
Yes, you can.
How can I add the code?
Okay, so what you can do is if you want, you can copy this waveform over, and I'm going to show you where in the survey it needs to be added.
Okay.
So
Thank you.
just hang on and we'll see if this answers your question. Okay, so we've defined our waveform. We've got our source waveform. In this case, it needs to be the source waveform object in SimPEG. So in this case, if you go under the time domain EM source namespace, there's a few different waveforms that you can look at. In that example that you just showed, Peng, by default, we always use a step-off waveform. So if you don't specify a waveform, we assume that it is just the current was on, and then at time 0, it shuts off. So there's a few different sources that you can look at, but here we're going to use this one. And then where that comes in is when we define our source. So before we do that, I'm just going to define the receivers, and then we'll look at where you can change the waveform for the source. So there's a couple parameters with respect to the source that I pulled out from the header file. So we know the area of the transmitter loop. And we also want to have the radius so that when we define our circular loop, we can specify that. The other thing we need is the system height. And in this case, our receiver is at the same height because they are fixed on the same system. So that's relevant for both. The data that we're measuring in this case are dB/dt data. So there's a few different receiver types that you can look at. If you're looking at a ground-based survey, you might look at electric fields, for example. But here we're just looking at point measurements of dB/dt. The first field here is the location of the receiver. So we put it for SkyTem, the receiver's at the back end of the loop. So it's basically sitting on the radius of the loop. So we offset it by that amount in the x direction. There's no offset in the azimuthal direction, right? Because we're on the cylindrically symmetric, that doesn't matter. And then in the z direction, it's at the same height as the system height. The orientation of the loop is in the z direction. So if you were looking at the x component data, you could change this to x. And then here we're going to look at basically all of the time channels until the latest 3. So we had a hard time fitting those in this example. So if you want, you can remove that and try and fit the data, see what you can do. But in this case, we decided to cut those ones out. And then we're going to shift them by that source where the source waveform starts, right? Because we start measuring after it's been shut off. So all of our measurements should be with respect to how we've shifted our waveform. Does that make sense, what this guy is?
Yes, but in the case that the data it's not that, how should we change it that when it's not the secondary field?
So in this case, oh, like if you have on-time data? Sorry, I don't know what you mean by the secondary field.
Like in this case, this is the survey, right? You are putting the data that you took from the file, from the field.
Yes.
In my case, in the example that I send you, I have the resistivity, not the dB/dt.
Oh, Claudia, I think then you need to know what kind of transfer function they have used. So there's a kind of like a semi-analytic solution that you can transfer your voltage to apparent resistivity. So you need to ask the provider of the data and how they actually transfer the apparent resistivity, like from voltage to apparent resistivity. What they have measured is supposed to be a voltage, not an apparent resistivity.
Yes. Okay.
Yeah. I think that's on your plate. So I think we can help, but we need some like exact information how they actually transform that.
And so that's actually true basically everywhere throughout SimPEG is we're always looking at like what are the actual field measurements. We don't invert for apparent resistivity or anything like that. So it's always like electric field measurements, dB, dt, B. So it is field values.
In her data, she has electrical resistance, which is volts per amperes. Is how I say. So, and you also have ohm to meter, ohm meter resistivity. But we also have electrical resistance. Can we use that one?
It's
No, I think you need to use the voltage.
yes, you need to find out how they normalized it. That's something that they should be able to provide you with.
What system are you using?
SandFast.
Okay, yeah. Yeah, we haven't used that system, but I think I'm pretty sure they provide the voltage as well.
Yes, they provide the voltage. I have.
Right, and the important part is the waveform. So I mean, I guess they might assume some sort of ramp off waveform. So you need to have that information, and you can put that into SimPEG.
É aquilo que eu fiz naquele exemplo, sim. Okay, thank you.
Okay. Yeah, so here you can actually look and see what the different types of receivers that we have are. So all I did there was did dot and then hit tab. So point B, dB/dt, E, H, J. So those are always going to be in SI units. And so that's what we work with in SimPEG. For waveforms, there's a couple of examples in the documentation. We're working on improving the docs. So like you can expect some improvements in the coming months. But as is right now, there's still some examples that you can use. So if you look at time domain electromagnetics, here's just a small gallery of a few different types of waveforms that we have. And so in a lot of cases, you can map whatever waveform you're working with to something that's similar to one of these. If not, we can help you define a custom waveform in
Claudia, the waveform that you need to use there is ramp off waveform. I think that's pretty typical for the ground. Yeah, that's a typical for the ground system. So ground team system, that's actually a typical waveform. So yeah, I would suggest to use that.
Okay.
Hi, Lindsay. Another quick question.
Yep.
So when defining your waveform, do you need to do a waveform used for time stepping, or just to define the shape?
Sorry, can you repeat the question?
So, yeah, what are you going to use a waveform for time stepping, or just use a waveform for like convolution?
Oh, we do use the waveform for time stepping.
Okay, so there must be some requirement for like a delta t, or like must be fine enough to.
Yeah, so like we can go into this in more detail, but basically the thing, like if you want to define your own custom waveform, all that we need is some function that given a time gives us a value back for that waveform. And so if you want to compute that like by doing interpolation between discrete points that you are provided in a waveform file, you can do that. But all we need is a function that basically given a time gives us a value of the waveform at that time.
Okay.
Okay, so I'm just gonna make sure I ran these. Okay, so then the next thing that we're gonna do is we're gonna define a source list. So if you were gonna do a 3D inversion, you might actually have a whole bunch of sources in this list with different locations. But here, because we're just doing one sounding, we've got one source location. And so we have one source in our list. So here we're going to use a circular loop source. The first thing that all of our sources take is a receiver list. So in this case, we defined our dB dt z receiver at this location. So we pass that in as a list. So we could have actually, if you're doing a ground-based survey, for example, you might have one source and multiple receivers. So we could have another receiver here, and that's no problem. You also don't have to define receivers. So if you want to just sort of look at the physics everywhere on the mesh, you can pass this as an empty list. But if we're going to do an inversion, you need to have receivers there. The location of our source, so it's centered at the origin at the same height as the system height. So the elevation at our receiver index. The radius of the loop, we defined that here. It's oriented in the Z direction. And then this is where the waveform is passed. So Peng, coming back to your question, if in the example that you're exploring, if you want to change the waveform, when you define your transmitter, you can provide a different waveform there. Does that make sense? Okay. So we define our waveform, and then we can also define a current. So in this case, the data that we were provided are normalized by the loop area. So again, I know that by coming back to the header file, and they've told us that. I forget where, but it is in here. And so in this case, we want the moment to be 1 of our loop. So I normalize the current by the area. Does that make sense? Oh, and
Yes.
okay. I mentioned this before, but I'll just bring it back again, just as we're going to set up the problem. There's a few different time meshes that come into play. So here, the receivers, they're listening at the time channels that were specified in the header file, okay? So this gives us basically all of the fields aspects of our forward simulation. We know where our receiver is, we know where our source is, and all of those parameters. So now what we're going to do is we're going to set up our discrete forward simulation problem. And so the first thing that we need to do here is we're going to define where the problem is evaluated in time. And so this is the same syntax as how we defined the mesh in the first place, because actually under the hood, we treat the time stepping as the same concept. It's a 1D mesh that has cell centers and cell nodes. So here we're going to take 5 time steps early on that are 5 time steps before the peak time. We look at the difference between the off time and the peak time. So there, and define 5 time steps through there. And then we have a series of time steps going from 5 of them that are 10 to the negative 5, 5 of them that are 5 times 10 to the negative 5, 10 of them 1 times 10 to the negative 4, and 15 that are 5 times 10 to the negative 4. So afterwards, I encourage you to go in and play with these, see how that changes the forward simulation. And here you can actually see, so I've just plotted, so we have our waveform like we did before. And then all I did was plot the times where we're going to evaluate the problem with these hash marks here. So you can see we've got 5 time steps before we shut off. We very finely discretize immediately afterwards, and then we expand a bit as we go later in time. Does anybody have questions about that?
Yeah, I have a question.
Yep, for sure.
You can see my screen.
Okay, 1 second.
Oh,
Yes.
can you see?
Yeah.
I want to change the time steps, but when I change these values, but it can't work in the next step. They can just use these values, but they cannot use others. Can you understand?
So this didn't work?
Yeah, this term doesn't work. Just this can work.
Okay.
I just changed some like here.
So okay, so that's a pretty big change. You've changed by orders of magnitude. When you say it doesn't work, does it error or did the results not look like they make sense?
What?
Does the code produce an error or like what do you mean by it doesn't work?
The result is here. When I change the time steps, they have not results. Just the DBDT results. They cannot.
Okay, so the computation is running, but what you need to be careful with when you run a time domain simulation is that you don't coarse in too quickly. And so in this case, when you jump by an order of magnitude, like we lose accuracy in the simulation when there are big jumps in the time mesh. So in this case, when you expanded it very far, then like sometimes the forward simulation breaks in a sense because we just can't accurately compute across that large time step.
Okay. Oh, if I add some value here, maybe it's work.
So play around with it and see, so you can start to get a sense for what a good time stepping scheme is for that problem.
Okay. Okay.
So can everyone see my screen again? Are we back online? Okay. So I want to come back to this cell again because there's a lot of stuff happening in here. So we've defined our time stepping, and now we're going to set up a problem. And so this is language that I think we're going to eventually change in SimPEG because it's a little confusing. But what the problem is right now, you can think of it as the physics engine. So it's all the machinery to actually solve the partial differential equation. And so here we've got a time domain EM problem. It's going to be solved. It is a 3D. It is a 3D problem because even though the mesh is cylindrically symmetric, we still have everything defined in three-dimensional space. We can still define what an X and a Y component are. So it is still a 3D problem. And then in this case, there's 4 things that you can solve for when we look at Maxwell's equations. In this case, we're going to solve for the electric field. And then from that, you can compute dB, dt, b, any like other fields that are derived from that. There's some more details on like why you would choose each one in the paper that we have. So if you don't have the EM paper that sort of outlines how SimPEG EM works, we can send that around to everyone afterwards. But in this case, yeah, we're going to solve for the electric field. Does anyone want me to go into more detail as to why you would choose different ones, or we can sort of table that discussion for now? Okay, I'll just keep moving on, but we can follow up if people are curious afterwards. So when we define the problem, we need to give it a mesh. So that's going to be how it figures out what all of the differential operators are. So when we have Maxwell's equations, we know we need to compute a curl on the mesh. And so the mesh object knows how to do that. We pass the time steps. So this
this mesh, it's always the same that I did before in the forward.
Yes, correct. This is the forward simulation mesh. So if I look at so then we provide the time steps. So that's going to be where the problem is evaluated. In this case, our mapping was defined from our set of parameters to electrical conductivity sigma. So we defined the sigma map as the mapping that we constructed. If instead you wanted to work in resistivity, you could provide a row map. And then you would be providing a set of mappings, or like a mapping object that takes you from your set of parameters to then resistivity on the mesh.
Hi, Lindsay.
Yeah.
Is there option for different boundary conditions?
Not for the EM problem right now, but that is something that like we'd be interested in implementing. So if that's something that you or your students are like curious to do, we can certainly chat about how to do that. The DC problem has different boundary conditions, so you can specify different boundary conditions for DC resistivity.
Okay, so here what's default?
The default are the natural boundary conditions.
Okay, thanks.
And then so Dequan, this is then where the solver, when you were asking about that earlier, this is where the solver comes in. So we tell the problem which solver we want it to use. So by default, it uses an LU solver that comes with SciPy. If you're solving any remotely, like moderately sized EM problem, that's going to be very painful. It'll be painfully slow. So like highly recommend that you use the Paradiso solver.
Okay.
So that gives us the problem. Then we also have to create this survey object. Why I'm sort of hesitating here is that we are going to simplify these steps at some point. So we'll explain that when it comes out. But for now, what you need to do is, given the source list, we create a survey. And the survey then knows how to create data when it's paired with the problem. So that's why we have to communicate basically all of the information from the survey about where the source is, what kind of source it is, to the problem, so that we can actually simulate the physics. And then once we've simulated the physics everywhere on the mesh, we then ask the survey, okay, where should I evaluate my fields to give you data? So that's sort of the back and forth that happens between those right now. So I showed you this before, but this is just plotting our time discretization, just to get a sense of where we should be discretizing finally, right? We want to make sure that we do a good job of these early times, and then we can expand as we go later. So Peng, when you're looking at designing different time discretizations, it's worth sort of plotting this out and seeing what your time discretization looks like. And then also, if you run a forward simulation and you see something that looks fishy, this is a helpful metric to have, because if we saw, for example, that a time, like there was all of a sudden a big jump in the results right here, right after we expanded our time discretization, we might want to go back and then actually do a better job refining in there. Okay, so now we've got all of our machinery that we need to perform a forward simulation. So what we're going to do is assign, specify what our observed data are and assign some uncertainties. Those will be used in the inversion. And then we're going to look at, from our half-space model, what do forward simulated data look like? So we use a standard deviation of 5%. That's pretty common. If you don't know what to do, that's not a bad place to start. And then here we look at, our decays are going down to about 10 to the negative 12. We're ignoring those last 3 data points. So let's choose 10 to the negative 12 as a floor. These are, again, parameters that I would encourage you afterwards to come and play with and see how it impacts the inversion. So here we take our data. So our observed data are going to be the SkyTem data at the receiver index, and then we ignore those last 3 time channels. So here I'm going to run a forward simulation. So we ask the survey for predicted data given our starting model. And this is a Jupyter-specific command that actually times how long it takes to run this cell. So it's helpful to have when you run a forward simulation.
Lindsay, that's double percent. I think that'll be really nice to run it like 10 microsecond.
No, double percent does...
I think that's pretty fast.
I thought double percent did time, like multiple runs.
No, I think that's time at.
I see. Okay. Double percent is
So
time.
do you mean oh, double percent also? Okay.
Yeah, so the single forward run here takes about like 0.5 second, 0.6 second. So which is not too bad, but the other one was like 6 microsecond, which
That's
was
very true.
really fast. Like, which would have been really nice.
That would be nice.
Sorry again. What's the difference here? Like the single percent, double percent?
We can look. I don't remember offhand what the single percent. I think it might actually just be oh, so it's better if you're using it, I believe, for like right next to a given line. So it looks like this makes sense. So it's looking at a line. So it only took like a microsecond to run this command. That makes sense. Whereas double percent looks at the entire cell. So right.
Okay.
So here, actually, if we ran this,
Yeah, that would have been fine.
that should be the same thing as the double percent.
Ah, perfect.
Good to know. And okay, so now we've got our predicted data and we know our observed data. So just plot those up. And so in this case, this forward simulation isn't actually strictly necessary in order to run the inversion, but it's a really good idea so that you can sanity check your entire setup. So for example, the first time I set up this notebook, I forgot to normalize the current by the area. And the difference between my predicted and my observed data was 3 orders of magnitude. So that's they shouldn't be that far away from each other. So then you can go back, check your forward simulation setup, and just make sure that everything is reasonable and we're in the right order of magnitude. This also shows us that our half space is not the best model, and we clearly have some progress that can be made by inverting these data. So does anyone have questions about running a forward simulation with SimPEG?
Hi, Lindsay. Why you have to flip the sign of dpret 0?
Good question. So in this case, when we're looking at SkyTem data, you will be looking at like the positive is going to be whatever is in the same direction as the primary field, right? Whereas SimPEG is always looking at like Z is always positive up. So in this case,
it's more like what you're actually measuring is a voltage, right? So if you actually like kind of keep track of what is a sign of the voltage, it's a negative dB/dt. So
I see.
You know what I mean? Like if you integrate the curl of E, that's like a line integral of the loop, and then you got the negative sign. So technically, what we're inverting for is the dB/dt. So that's the reason.
Because I forgot you're actually solving for the E, not for the magnetic field. So
yeah.
Well, but that doesn't
matter.
That doesn't matter. So you could equally change this out and solve for B. And you would still have to flip the sign. Because what SkyTem provides you is voltages, and here we actually look at what is dB/dt at the receiver location. And because it's going down, it is negative.
Okay.
Whereas the voltage that's provided is positive.
Okay.
That makes sense?
Yep.
Okay. So, and that's also a good point here, so that when we actually set, so now we're going to start looking into the inversion and setting up our inversion. So when we set our observed data, we want to make sure that the signs are consistent, right? So we know that here I actually had to flip the sign in order to get what we wanted. So when I set the observed data on my survey, I'm going to flip the sign here so that we don't have to mess with anything on the receiver side of things.
So inside the code, in order to get dB/dt, basically just take integration along the loop?
In this case, we look at a point. So like we're treating the receiver as a point receiver, so we're not necessarily integrating, but we have taken the curl of E to get to dB/dt.
Okay, I see. Okay, thank you.
Okay. So we set our observed data on the survey, and then we construct a data misfit object. And it needs to know about the survey because it needs to know what data we're trying to compare to. And then here, based on the uncertainties we set up here, we can set the weighting matrix. So the next thing that we do is we're going to set up a regularization. So here, we need to actually create a different mesh because our model parameters don't actually live on the full cylindrically symmetric mesh, right? So we want to regularize on a 1D mesh. So here, all we've done is create a 1D mesh that is only for the active cells. So let me just comment this out and I'll show you what that looks like. In this case, it's just a 1D mesh. I should probably give you nodes. So those are the nodes of the mesh. So here it's very fine near the surface. And then as we go down, they expand. So we pass that then to a regularization object. Here we use the Tikhonov regularization. So we give it a mesh. In this case, we don't actually need this mapping. I'm going to delete that because it's not necessary. But I'll tell you what you could use it for is if you needed to like transform your model in any way to get it onto the regularization mesh or change what you're regularizing, you could use it there. You could use a mapping to do that, but we don't need that in this case. And then here we can set our alphas. So alpha S.
Sorry, Lindsay. Could I use the same mesh that I use for the forward?
No, not in this case, because the regularization is on the set of parameters that we're inverting for. And so in that case, they only exist in 1D, right? Because we're only inverting for log conductivity below the subsurface. So we need some sort of mesh that we can regularize those values on. And
okay,
so yeah, so they don't live on the full 2D mesh. So here, the way I constructed the regularization mesh is by grabbing the cell widths from my cylindrically symmetric mesh in the vertical direction, and then grabbing them only at the active cells.
So the regularization mesh has to be the same number of the cells that the active cells for the forward.
Yes. Yeah. So it's the same length. It's got to be the same number of cells as our the model that we're inverting for. So here, if we look at, I'm just going to run this. So if we look at the length of M0, which is our model, and we look at reg mesh, these two numbers should be the same.
Okay. Thank you.
No problem. So the Tikhonov regularization, the way we define that is we're going to work with a smallness term, which just looks at the difference between our model and our reference model. So in this case, we use a reference model that's the same as that half space starting model. And then alpha x, because it's only in 1D, we always treat x as the first dimension, y as the second dimension, and z as the third dimension. So in this case, we only have two components to the regularization because it's 1D. So we have the smallness, and then we have one derivative for smoothness. So we're then just looking at, okay, if we compare the value near the surface to the next cell over, how far apart are those values? And we want to minimize that derivative. So we penalize it.
The smallness is how to smooth the model to not be so different, to not change too different, too fast.
So that actually is more the smoothness term. So that's going to be what this controls. So the alpha x basically says try not to introduce big differences between adjacent cells.
Okay, so the S is?
S is smallness.
Oh.
So what that does is it basically says, okay, how close is my current model to my reference model?
Okay.
Okay, I'm forcing my model to the reference one. Okay.
Yeah. And the MT tutorial has a good explanation and examples of what happens when you play with these. So I'd encourage you to look at that one and then flip back to this one and mess around with these parameters and see how it changes the inversion result.
Okay.
Okay. So there's a lot of details here, and the MT tutorial does a good job of explaining what each of these parameters are. We can copy some of that over. And actually, one of the things that I would really appreciate after this tutorial is if you do come in and work with this notebook and you make notes and explanations of what's going on, if you would be willing to contribute that back so that other people can benefit from what you've learned and what you've documented, that would be fantastic. So we can chat about that after. Okay, so we've defined our data misfit and our regularization. And so now we're going to define some optimization machinery that we're going to use to solve the inverse problem. So in this case, we're going to use inexact Gauss-Newton, and we specify the maximum number of iterations to be 10. Here, I think that's the default anyways, but the line search shorten, what that means is if you try and take a step, but the inversion finds that the value of the objective function actually increases rather than decreases, it's going to say, okay, let me take a step that's half that length and we'll try that again. And then it continues taking a step that's half the length until we get to something that actually does decrease the value of the objective function. The opt.remember, what this is doing is it's going to remember, this is terrible notation, but it's going to remember the value of the model at every iteration. So if we wanted to go back and look through the different models, we could do that afterwards. Otherwise, it will forget them, and the only thing that you get out is the end model. Okay, so then we set up an inv-prob. So conceptually, you can think of this as basically the statement of the inverse problem. So we want to minimize some data misfit plus a regularization using some optimization machinery. The other thing that I wanted to mention with the max iterations is if you are going to do, so for example, if we were going to run a stitched 1D inversion where we're going to invert a whole bunch of different soundings and then bring them all together to make a 3D model, it's often helpful to set this value to be like relative, to be constrained, so 10 or so that you don't actually, those individual inversions don't run for too long. That's all. Okay, so then there's a couple things going on here. So here we'll set a target misfit. So we want to stop the inversion when we hit the target misfit. So if you don't know what that is, we can check out the docs. Let me do. So I don't know if you've seen this, but the question mark in the notebook actually pulls up documentation. The double question mark, I believe, brings up the code. So some of our documentation is lacking a bit, and so sometimes it's helpful to actually just have a quick look at the code and see what it's doing. So here we specify a phi d star, so that's our target misfit, and that's based on the number of data that we're looking at. And so you can check out in the paper, we describe a bit more of why you might want to use that. But here you can play around with this inversion and try running it beyond that and see what happens. So the MT tutorial, again, talks about this stuff in detail. We also set a trade-off parameter. So in the inverse problem, we need to tell it how to combine the data misfit and the regularization. And so we often want to have some sort of weighting between those. So here we set it to be a fixed value of 5. You could also estimate it. And so we've got some utilities that will try and estimate based on sort of how big your regularization term is and how big your data misfit is. Choose a reasonable beta between the two of those. So again, I would encourage you to just like come and play with this stuff because I think that's the best way to get a sense of what it's doing.
Do we have the auxilio of the L curve to find this beta?
So yeah, to find the beta, like you can use the L curve method. So that then means you're going to run an inversion. So the MT tutorial does this. So you run an inversion at a whole bunch of different betas, and then you actually pick the one that's at the elbow. And so yeah, check out the MT tutorial for that.
Okay, but SimPEG also, I can also do that with SimPEG.
Not automatically, so we don't have like an L curve automated. Yeah, so that's one that you would need to, like, you can find it manually yourself, but all the machinery to do that is in SimPEG.
Okay.
Yeah, and then like sort of the automatic picking that we have in SimPEG is this beta estimate by eigenvalue. So it basically tries to estimate like how it takes a random vector and multiplies the regularization by that and the data misfit by that and says, okay, how big are each of these? And then based on that, I can choose some ratio between them. So maybe I want them to be equal. So that's what this would say. Or if I wanted the regularization to be 5 times more important than the data misfit, that's what this would say. Okay. So here, then we create an inversion. So it takes the inverse problem. So this is like just the statement of the thing that we want to optimize. And then it takes any directives that we have. So basically those are like controllers on the inversion. So in this case, the target misfit is a controller on the inversion, right? You want to check in at every iteration and say, have we hit the target misfit? If yes, stop. If no, continue on. So that's an example of a directive. If you wanted to use the beta estimation, that's also a directive because what it does is says, okay, at the very beginning of the inversion, try and estimate a reasonable beta for this inversion and then go. So there's a few other ones that you can look at, but these are probably the most common two that we have. There's also stuff for saving models and outputs and things like that as the inversion runs that are sometimes useful if you want to have that written out to a file. And then here, once we have our inversion object, all we have to do to run it is run the .run method given a starting model. So here we can do that. So there's a few things that are output. So we see beta here is 5, so that's what I set. We can look at phi d. We see that it's decreasing, so that's good. And we can see the value of phi m, our regularization.
Lindsay, one of my problems with my code is that so you achieved our target misfit, which is phi d equal to n data, right? Number of data.
Yes, that's correct.
Okay, so one of the problems with my code is that phi d doesn't converge. So it's stabilized like in the 9th iteration, it's stabilized. Do you have an idea why this happens?
So in that case, you might need to look at, so it looks at phi d, and one important thing that's coming into phi d is what your noise model is. So it's quite possible in that case, if it's stabilized, that maybe your uncertainties are too low. So it's trying really, really hard to continue fitting the data, but it's made as much progress as it's going to make. So that's one possibility.
So the uncertainties, do you mean STD, standard deviation?
Yes, the standard deviation. So here, the standard deviation and a floor. So here we defined our uncertainties as some percentage of the observed data plus a floor. So these are parameters that you might want to play around with and see how that impacts your inversion.
Okay. Can you explain me what is the floor? I never understood it very well.
Yeah. So in this case, it's probably not quite as important, but in places where you have sign changes in your data, it's very important because you want to make sure that you're not trying to fit. So if DOBS is 0, you don't want to fit that exactly, right? So
Okay.
4 basically gives you, it says, you know what, my 0 is 10 to the negative 12. So don't really worry about anything that's less than that. So in this case, we've basically sort of set, sorry, I'm looking for the data plot. So here, 10 to the negative 12, we consider this to be like
Okay.
nobody's level. So we're not going to get anything more accurate than 10 to the negative 12.
Okay.
Thank you.
Thank you.
All right, so this one converged in 2 iterations. But if you go back and play with different parameters, you can see how that changes. And then here, we want to actually look at the predicted data. So we ask the inverse problem, what was the predicted data at the end of the inversion? And then we'll compare that to the observed data. So here we can see we did a very good job fitting that, with maybe the exception of like the very first time channel. And then we can see what the recovered model looks like. And so here the MREC was what we asked, what we named the recovered model from the inversion. So that's in one inversion with SimPEG. Do you have questions about these last few steps or about the general workflow? Yeah.
For this example, looks simple. It's more difficult when we are doing. And that example that I send you, I have some results, but you say something about the signal of the data, that you multiply the data 4 minus in this notebook. The observed data, you multiply per minus 1 to change the signal.
Yeah, and that was just because of like sign convention differences between what was provided to us, which is just a voltage, versus dB dt in the positive Z direction. And so one of the best ways to sort through some of these things is to actually just run a forward simulation with a model that you think is somewhat reasonable for your area. So in this case, we did a half space model, and plot that against the observed data. And so if you see that the signs are completely different, or that you're off by a couple orders of magnitude, those are all indications that like there's a parameter that's not quite right in your setup.
Yes, I think probably I have that because my sinus, it's the opposite. I have one positive and one negative. And because that I was asking you why you multiply per minus 1.
Yeah. So in this case, it's sign convention differences between like dB dt in the Z direction and the measured voltage. But yeah, in your case, it could be sign convention differences there too. So yeah, forward modeling is a very useful tool for figuring these things out. Sagi, were there any things that you wanted to add from this inversion?
Not really. That was good. But the not sure what's the like a configuration of the tempest. It's if that's there's an offset between transmitter and receiver. In the early time, you can get some like a sign reversal. So yeah, it depends upon the geometry. It was just a comment.
Yeah.
So does this code invert the data with the offset?
Yes. So in this case, let me share my screen again. So I mean, they could be coincident, or they don't have to be. And so when we set up the receiver, we specified its location here. So we offset the receiver from the origin, which is where the source is located, by the radius. So they don't have to be coincident.
All right.
Okay, I will just share my screen with you just to show you the result that I have with the tempest, because I already inverted some data, but for me, the result it's not good. It's not makes sense.
All right. Oh, it looks like you just went mute. There we go. Okay. Oh. Oh, I see. Okay. So you're muted right now, so we cannot hear you. Okay.
Okay.
Yeah, we can hear you now.
I did this inversion with the canvas, and I have this problem because my the observed rate it's not similar to the predicted data.
Yeah, so it looks like, I mean, there's several orders of magnitude difference there. So in this case, like coming back to what Sagi was saying before, like, is this apparent resistivity, or because it needs to be converted to like a voltage to work with dB/dt. Sorry, your data are dB/dt, or what are your data?
My data is voltage per ampere.
But it looks like the data, the observed data and the predict data are having different signs.
Yes, they have different signs. I put here both of them, and also the magnitude order.
Yeah. Yeah, so in this case, these are things that like need to be sorted out before running the inversion, because we're clearly not forward modeling the same thing as what the observed data are. So in this case, that requires some work looking at just comparing forward simulations and trying to understand, first of all, what are your data and how do you translate those to dB/dt or to electric field?
Here, I do not understand this part if I did this right, the dB/dt, because you also have other parts, other options to put here.
So that one just quick note, I always try and provide like the keywords just for myself. So like, times equals T obs. But that looks correct. So, but it is then just a question of like, is what you're stating are dB/dt data? Like, are your observed data actually dB/dt or not?
My data is not dB/dt.
So when the inversion's running, it's expecting dB/dt because when you specify the receiver as a point dB/dt receiver, it is then expecting that it is going to try and compare itself to something that is equivalent, so dB/dt data. So if the data are not that, then like the inversion is going to struggle or do something nonsensical because we're not comparing two things that are equivalent.
Those are my data. I'm using this one.
Okay. So like it's sort of, sorry, go ahead, Sagi. I think you're gonna jump in and say something.
No, Lindsay, go ahead.
Oh, okay. So like sorting this out right now over the screen is a bit tricky. But what I would encourage you to do is take a look at sort of just running some forward simulations. See if you pick a single location, can you actually get data, D observed and D pred, that are behaving similarly? And that's the first place you have to start, is make sure that what we're forward simulating actually is the same thing as what the observed data are expecting.
So in the SimPEG, I have to put the dBdt from my equipment. I have to find a way to convert the data to dBdt. This is the input data for SimPEG.
Yes. Yeah, we expect the dBdt data.
Okay. So in this case, I just try to convert the data for dBdt.
Yeah. Okay. Well, we're coming up on just about 2 hours here, so I think we should try and wrap up. If there aren't any more specific questions about this, what we can do is anybody's welcome to post questions on Slack. Are you all a part of Slack?
Yes.
Okay. That is a good place to reach us with any sorts of questions or things like that. So as I mentioned before, if anybody is willing to work through these notebooks, add notes, so like have a look at the MT tutorial and add notes from there, explain some of the steps of what's going on. That would be an excellent contribution back to SimPEG, and other people can then use this as training material. Because often, we're so used to working with SimPEG, we forget which pieces are stumbling blocks. And so if there's something that you have a question about and that was clarified and you can make some notes on that, that would be, a wonderful contribution. And you can reach out.
I had the results. I can also share the notebook, the 10FAST notebook.
That would be awesome. That'd be really exciting. Yeah, absolutely. So so feel free to ping us on Slack and reach us that way. We do SimPEG meetings every Tuesday. So today it'll be at 2 p.m. So anybody's welcome to join, but they're also live and we have notes afterwards. So if you can't join because of time differences, because I know we've got the world covered at this point. So yeah, you can watch asynchronously and reach us on Slack. So perfect. Well, thanks everyone for taking time to be
For
here.
your attention, for explaining us, it was very helpful.
I'm very glad.
Thank you for the availability.
Perfect.
I hope we can
Thank you
also
so much.
Thanks, Lindsay. Thanks, guys.
Thank you.
Thank you, Lindsay. Bye. Bye, everyone.
Bye-bye.
Jack, you're muted. Nice talking to everybody. Bye, Jaquan.
Bye.
Bye.
Bye,
All the best.